Well, let's rewind back to history. Year 1874 marked the release of the world's first commercial keyboard in the form of a typewriter. Sir Christopher Latham Scholz produced and patented the design of QWERTY, named after the first 6 letters that appeared on the keyboard. Technological advancements in the past 150 years have gained great heights, but the layout has remained unchanged. But now I think at this point of time it might be a good idea to set this keyboard on a journey of evolution. Maybe we can find something better. Well, for a phenomenal typist, the use of 10 fingers for typing is really common. By the definition of a perfect keyboard, it should take the least distance for our fingers to move to type a word. As per International Typing Agenda, the fingers are positioned at particular places known as the home keys. A typeword starts at this position before moving the finger presses to the other keys. To analyze the map of a commercial keyboard, we need to create some key distance mappings. In terms of Python programming, we can use to create a 10x3 matrix which would contain the keys for us, and we can use the corresponding index values of the keys to map them into a dictionary. As I have said before, a typist begins with the fingers at the home keys. Now to type the word pool, our fingers have to perform certain maneuvers. Finger 10 moves from semicolon to P, finger 9 moves from L to O, finger 9 then stays at the same position and presses O again. Finger 9 then comes back from O to L. This entire movement process is of 3.096 units of distance according to our key distance mapping. But such a short sentence would not suffice the purpose of our code. To train a model to generate the best keyboard layout, I would be generating a genetic algorithm. For that, I will use a famous quote from the Macbeth: "Fair is foul and foul is fair. Hover through fog and fill the air." To type this sentence, our finger travels a distance of 38.615 units. In this case, if we consider our DVORAC layout developed by August Dvorak and his brother-in-law William Daly in 1936, the total distance traveled to type the same is 30.56 units, which is conveniently lesser than our QWERTY keyboard. Now if we use a bigger paragraph like 3905 words from Kaggle, the QWERTY layout yields a total distance of 3000 units, while the DVORAC layout yields the same for 1.6k units of distance. We can thus conclude that the DVORAC layout is in fact more efficient than the QWERTY layout. Instead of creating more paragraphs, now let's create some randomly generated keyboard layouts. It's easy to shuffle a two-dimensional list, taking in the fact that shuffling is happening in the entire keyboard layout. This algorithm helps us to generate the most random possibilities. We can then calculate the distance for them. According to our genetic algorithm, the keyboard generated belongs to the first generation of creation. Each key of the keyboard is a gene. Each keyboard itself could be referred to as a chromosome, and all the keyboards together would be termed as its population. Our population size is 10. Total distance formed by each keyboard would be referred to as its fitness score. After we calculate the fitness score for each chromosome, the best results are selected and passed on as in the form of natural selection. Furthermore, we select 2 keyboards as the parent and split point in one of them. We add the keys from the left side of the parent to one side of a keyboard and then the remaining keys from the second parent in the hope of getting a better keyboard. This creates a 50% chance for a perfect combination. From the new keyboard layouts that have been found, we shuffle the keys and form the second generation of the keyboard layout. With this process, we select the 2 most efficient keyboard layouts from our generation and continue to run the loop, creating more of them. I had run the algorithm a couple number of times, and these are the best results produced. The layouts are pretty much similar, with an average fitness score of 1196 units of distance. I named the newly generated layout LATER, since the letters appear in the middle row of the keyboard. If I compare it with the previously attended results, the latter layout is no doubt the most efficient of all. I shall not say that this is a perfect keyboard, but for experimental and training purposes, the algorithm serves well. Genetic algorithms are actually fun working with.